Gonna be a mic check. So we're live in YouTube, but how is can you listening how it sounds like? Because I'm not sure which the mic that the system is using at the moment. Can you hear it at all?
I don't see the.
You don't see the streaming? The streaming should be on.
Yeah.
So it's on. Okay, can you listen my voice? So is the mic all right? So it's all right. Good. Simulation of a mechatronic machine, lecture number 4. This is how we can get started. Remember the way that we say, hello, how are you doing? This is the way we do it. Today, we're going to just get started from that coordinate system, because last time, right after my lecture, there were still some doubts, like how is that you can actually conduct rotations in 3-dimensional space. So we will go back to that, but the main body of today's lecture will be related to numerics. So we will look at how is it we can conduct the first analysis. The first analysis that we will conduct today is a kinematic analysis. And again, kinematic analysis you can carry out if you know if your system have a 0 degrees of freedom. So if you have equal number of equations and unknowns. So unknowns we're dealing with are generalized coordinates. Equations that can be used to solve these unknowns are constraint equations. So in order to make these things to match, in order to solve that system, we have to have equal number of equations. That's constraint equations versus unknowns. And unknowns are generalized coordinates. So that's how we can make this happen. In reality, so we have to solve the kinematics in position level, which we will conduct by using iterative method. And in iterative method, we have to compute something that is called Newton difference. And with help of the Newton difference, we can update our generalized coordinates with a certain number of iteration, we can get the solution at position level. Then in velocity level, by the way, where the camera is actually pointing out, I'm not in a camera. Hold on. Is it a frozen or? So it's frozen. So the camera is frozen. So let me try to put it back on. Don't know why it is doing this. Okay, still nothing. Let me take a cable off and put it back. What about the integrated camera? Oh yeah, integrated camera is all right. And I'm back. All right, so the kinematic analysis. So we need to conduct that in a position level, in velocity level, and finally in acceleration level. And that's those 3 levels we need to do in one particular time. And then we're going to increase the time, and we're going to redo the whole set. So that's how it's going to go. And again, the information we need in order to conduct the kinematic analysis will be the constraint equations only, nothing else. So in kinematic analysis, we don't speak about the forces. It is just a motion analysis, nothing else. So far, few important things that I would like you to know. So I would like you to understand the difference between the particle and the body. You know the difference? The particle is a one mathematical definition without dimension. And the particle don't have a rotational degrees of freedom. Body consists of infinite number of particles, and we can define them by summing up all the particles within the boundaries of the body. And now, the next thing that I would like you to learn is a kinematic analysis. And you must differentiate the kinematics and dynamics. In dynamics, we have to deal with the forces, whereas in a kinematics, it's all about the motion. It's just a motion analysis. All right, but prior to that, let's discuss a little further about coordinate systems. Well, and hold on, let me put this bigger, a little more visible for you guys. So let's look at this one here. Let's hide this. Is this all right to you? All right, so I took a few pictures just earlier today when I was preparing myself to today's lecture. And I wanted to look at the two possibilities. You know, last time I said that, you know, we all a big fan of left-hand coordinate system. And we always love, whatever we wanted to do, we always love this left-hand coordinate system. And some of the participants say that, okay, I don't really like the left-hand coordinate system. I prefer to use a right-hand coordinate system. Either way, doesn't really matter. And let's just summarize, you know, what are the differences. You know, the one in left, of course, is a left-hand coordinate system, and it's based on your left hand. You know, left-hand coordinate system, it goes in such the way that the thumb is an X. This finger, what is this finger? Index. What's this one? Middle one. Yeah, the middle one. The middle finger. So the index, so the thumb is X, index is Y, middle one is Z. So that's the coordinate system. That is a left-hand coordinate system. Positive direction is defined by your right hand. So you take your right hand and you use your thumb to attach that to, say, one coordinate axis. Your fingers will tell what's the positive direction of rotation. All right? That's first alternative. Look, you know, we have the gang on. We're all doing this. What is an alternative? Well, that's, of course, right-hand coordinate system. Right-hand coordinate system is X, Y, Z. So it's, you know, pretty much same procedure except we change the hand. Now this time, you know, the thumb, again, you can use your left hand to figure out what's the positive direction. But the thumb have to go out from the axis. Out from the axis, your fingers will tell the positive direction. Is this how you've been teaching in Germany? This same way, the same way. That axis. Okay, because I checked this, I must admit something.
The other way around.
The other way around, that's the way it goes. Okay, so you're with me then. Okay, so let's summarize. So left hand, so this is a coordinate system, it always goes X, Y, Z. This one is the system that tells you what's the positive direction, thumb out. Excuse me, I made a mistake. So of course, thumb in this left-hand coordinate system. So your right hand, thumb in. That's the positive direction. Clear? We're gonna change the right-hand system, then the thumb out. Thumb out will tell you what's the positive direction. Okay, let's see how we're gonna work this out because, and I lost my pen. Here's my pen. So this is an exercise we discussed last time. Okay, we wanted to rotate the system around the y-axis. Remember, I provide this as a weekly assignment. I said that, you know, introduce the rotation around the y-axis, and I think the amount of rotation was defined as a p divided by 6. Was that correct? Okay. So now, if this is your assignment, actually the coordinate system, final configuration of the coordinate system should look like the one that is depicted here in the lower right corner. So that's what's supposed to happen. This is what you're aiming for. You know, I need to apologize that this is, you know, cut it a little bit, but the y-axis is pointing this direction, x is here, and z is here. And I'm rotating the system in such the way that, you know, this is the final configuration. You agree? Do you agree? The problem we have in Euler angles, the way we learn it, is that we don't have a rotation around the y-axis. That's non-existent because the sequence we learn is z, x, z. So y is missing. And I claim a few weeks back that when you use this sequence, you can put your coordinate to any orientations in space you want. And I wanted to demonstrate that even when you have this sequence, you can have this same configuration. How it's going to go? It's going to go in such the way that you introduce the first rotation, which is this famous variable phi, it was close, phi, which is p divided by 2, and you're going to do that in a positive direction. So what will happen as a consequence of that? You know, that's my original configuration. Now, due to the rotation, x-axis is now pointing in a direction of y direction in original configuration. You see that? All right? That's how it looked like. Now, what I will do next is that I will do my rotation, which was this p divided by 6. And I'm going to do that positive direction. Hopefully you can see that. So this is a positive direction. Right? This is the configuration due to that p divided by 6 rotation. All right? But now I have a problem because I introduced this first rotation, this one here, just, to replace x-axis or put the x-axis in the direction of y-axis. That was the only reason. So I have to compensate that. And the way that I compensate that is that I will do my final rotation, which is a minus p divided by 2. So there's supposed to be minus here. So I'm taking again the whole of z-axis and put it back like this. This is my final configuration. And now, of course, I understand that this is not really my drawings are handmade drawings, so they are not really scientific drawings. But if you compare this one and this one, that's what happened. So I was able to reach the final configuration. You guys agreed? You agreed? Again, all right? So, okay, from the beginning? From beginning, okay. So let me take everything off. Let me get started from the final configuration. So as an assignment, so we wanted to rotate the system along the axis that was mentioned like this. So it was 0, 1, 0. So clearly this is a y-axis. And we wanted to introduce the rotation that was amount of p divided by 6. All right? Problem in our sequence of Euler angles is that we don't have a rotation around y-axis. This y-axis, so this is a y-axis. This is what it means. Okay, we don't have this rotation. So we can still do it. And the way we can do it is that we will introduce the first rotation in such the way that original x-axis pointing this direction will be transferred to this direction where the original y-axis is located. All right? How much I have to rotate to make this happen? First rotation is z rotation, this direction, positive direction. It's going to be 90 degrees, p divided by 2. All right? What's my configuration after that? This is how it looked like. That's my configuration. Now the x-axis is pointing the direction where the original y-axis was located. All right? So now I'm ready to do my rotation, which was a p divided by 6. Okay, let's make it happen. P divided by 6. This is my positive direction. This is a result of my p divided by 6 rotation. You with me? Okay, that cannot be the final solution because my first rotation was just just assisting me to replace this axis. And I need to replace the axis back. How can I make it happen? I can compensate my first rotation by introducing the final rotation, which is t minus p divided by 2. Same amount than this, except that is a minus direction. So I put it back. And when I do that back, this is how is my final configuration. And when I compare that to this one, this seems to be all right. You're with me? We all agree? Yes, sir?
I think you told us it's different when you change the order of the
Order of rotations. Okay, so the positive direction is still something that confuses you. Not sure. Okay, so let me put this a little bit of writing to as an extra material to Moodle to clear this up. All right? Because I have another slide for you. And another slide is this one, right-hand coordinate system. Right-hand coordinate system, and I will do the same using the right-hand coordinate system. Now look at this is how the coordinate system looked in the very beginning. All right? And again, now I wanted to do the rotation around the y-axis, which was the p divided by 6. So this is how it should result. Right? So this is another different coordinate system. This is a right-hand coordinate system. All right, so my first rotation, I will introduce the rotation around the z-axis. And the positive direction this time is this one here, this direction. Okay, what will happen is that the x will point it out this direction, y will point it out this direction. All right, this was just to replace x by y. Change the x and y axis. All right, now I'm able to do my rotation, and my rotation is this one here, which is p divided by 6, and then I go and do my final, rotation, this time minus p divided by 2. This has to be minus, and I put it back, compensate the first rotation. And this one here and this one here visually look same. But to clear this up, I have another course that will be organized next semester. It's starting in January. And by the way, if you make a list about really outstanding courses in this university, that course that I'm teaching starting from January, that is really outstanding. It's super enjoyable course because it's all about how to apply the multi-body dynamics to gamification, different kind of product processes. So it's not that much about the theory, but it's more about applications. So in that course, I will get back to these rotations just shortly. And from that course, I will send that information to you, for all of you guys. You all right? Okay, because I would like to move on a little bit and discuss about something else. A little bit about summary of the previous lecture, and then I would like to go on and look at how is a kinematic analysis. Are you guys comfortable with that? You're comfortable with that. Okay, so the last time, but remind me please, sir. So can you please remind me that if you don't see this document in Moodle, say within a week, send me an email. Okay, so could you be our reminder officer? Good, put it in your CV. Awesome, okay. So last week we discussed about redundant constraints. Redundant constraint, that's something that the constraints are not independent, but they are independent. They are actually eliminating the same generalized coordinates, and they're affecting the generalized coordinates in a similar way. And if that's the case, that's mathematically redundant constraints. A redundant constraint is something that is not a good modeling policy, and you should try to avoid that as much as you can. And you can easily end up to have a redundant constraints and redundant multi-body system in 3D. And that's simply because of the nature of 3D. So pay a particular attention when you're making models in, say, Atom software, because one thing we're checking when we are evaluating your simulation assignment is what's the number of degrees of freedom, and try that to match to reality. Don't make a system that is a redundant system, because that's something that we will give a little bit of penalizing for you. So avoid the redundant systems in this course and in life. In life too, because they will not benefit you. They instead makes the interpretation of reaction forces that is coming from the constraints, they make that interpretation very difficult. So that's why we wanted to avoid the redundant constraints. Then a note from week 2. There was a note. One of you noticed that there was a typing mistake in week 2. There was this example where we introduced the revolute joint between the two bodies, the body A and the body B, and there was a typing mistake. This was in the original slide, this was written as a cosine theta, and it should be sine theta. Thanks for that. So who was that? Extra, I don't know, what is that we can offer because of that?
Extra point.
In exam?
Yes.
Okay.
Yeah, actually I missed the first assignment because of my personal issues, so you can give me points for that.
Deal. So we have a deal.
Yeah.
Okay, you happy with that?
Yeah, totally.
I think that you made a bad deal because the points in exam would be better deal, but now we have a deal.
Yeah, I still get my points from that.
Okay, all right, fine. So thanks. So if you notice that there is typing mistake, which happens, and the reason why it happens is that I'm a big fan of something that is called Control-C, Control-V. That's copy-paste. So usually the way I write this equation is copy-paste. You do that, you end up to have a lot of typing mistakes. So If you see typing mistakes in my slides or lecture notes, let me know, and I will give you a prize some kind, depending on the case. Okay. All right, so that was 2 weeks back that happened. Then shortly last week we discussed about kinematic analysis. Like I mentioned in the very beginning of my lecture, it consists of 3 steps. First one is a position step. So we have to figure out generalized coordinates, which is positions of our bodies, position configuration of our system. So we have to solve vector of generalized coordinates based using this first step. And the vector of generalized coordinates, that includes all the generalized coordinates, T1, T2, all the way to Tn. So once you know that, then you know the full configuration of your system. That's what we're aiming for in the first step. Second step, we have to solve the velocity. The velocity is this one here, q dot. Velocity of generalized coordinates. So once you know that, then you know how is the velocity of your system. Then we're going to go one step ahead, and finally we have to solve the acceleration, which is a q dot dot. So once you know the acceleration, then you're ready to move on the next time step. You increase the time, and you redo the whole thing. That's how the kinematic analysis will go. And based on what I just mentioned, there is absolutely no way to understand the details. But today we're going to practice the details. So we're going to look first, how is that we can solve this position level, which mentioned here that is a little bit of challenging. But it is a challenging because we need to use numerical methods to make that happen. The next one is very straightforward, which is a velocity state. That's easiest, clearly the easiest. It's simply a substitution problem that we have to do there. And then the acceleration is not as simple as velocity, but it's all right. Way more easier than the position level. Okay, so that's what we have to do today. And so this, as mentioned, the first step is critical one. That's the most critical step to take. Once that is covered, then it's more or less downhill after that. Okay. Kinematic analysis in position level. Position level, everything is hidden to constraint equations. We have certain number of constraint equations, and constraint equation can be written in such the way that we have first constraint equation, which is a function of generalized coordinates and time, and that's equal to 0. Then we have second constraint equation, which is a function of generalized coordinates and possibly time. Not necessarily time, but it could be a function of time. And that's equal to 0. And then we have all the way here to n coordinate system, and it is generalized coordinates and time equal to 0. Altogether, this is set of nonlinear equations, nonlinear algebraic equations. And what we have to do there is that we have to solve this guy, this generalized coordinates. That's our aim. That's an ultimate target we have here. And like I mentioned in last week, there are many methods to make it happen. We're going to use something that is called NewtonRaphson Method. Have you ever heard this method, NewtonRaphson Method? Never heard that before. You sure? I'm quite sure you have heard that. Go back to your math class notes and check it out, your books, and I'm sure you have heard something called NewtonRaphson Method. It is very often used method to solve set of nonlinear equations. Right? That doesn't matter if you haven't heard it before, because I'm going to explain the method to you today. So we're going to look a little bit about the theory behind the Newton-Raphson, but the main idea is to solve something that is called Newton difference. And the Newton difference is this one here. It tells how is that I'm supposed to update my generalized coordinates to find a solution. And I'm going to solve this Newton difference from this equation by simply taking this guy here and putting that in the right-hand side of the equation. It's going to be simple like that. But the notation that I'm using here are quite bad, because what are these components? They are not scalar components, but these will be, this guy here is a matrix, this guy here is a vector of constraint equations. So I have to have a matrix, and I have to invert the matrix. But what is this matrix, and how that is related to multibody dynamics? That's what we're going to look at next. All right? So let's look at this numerical method to solve the set of nonlinear equations. And we're going to, now this is going to be very bad what I'm explaining here. This is, deep in the math. But don't get confused about mathematical details. Because really what we wanted to have is this one here, Newton difference. And Newton difference is kind of like a map. It's like a GPS system for us. The GPS system tells where to go in order to reach the equilibrium, in order to reach the solution. So we get the first, GPS coordinates, which is this guy here. We will go another location. We will compute if this is our final destination or not. If it is not the final destination, we will move again. And now by moving with the certain steps, we can find the final destination. All right, so that's what we're aiming for. And now, in order for that to happen, we have to get started from the constraint equations like they are written here. So we have, keep in mind that this is a vector that includes all the constraint equations. So everything is in this vector. From 1 to n number of constraint equations. And they are a function of generalized coordinates and possibly time. All right. Now what I will do then is that I will introduce a small displacement to this coordinate. So I'm adding a little bit something to my generalized coordinates. And that little bit something is called delta Q, Newton difference, that we will call later that. Okay, so Newton difference will be added to that. And then we're going to go back to mathematics, and we will take a look at something that is called Taylor series. Using the Taylor series, we can write this equation as shown here. So we have here first the vector of constraint equations. And then we have here something that we have partial operation of constraint equation with respect to variables we're looking at. Again, variables we're looking at, what are those? Generalized coordinates, correct. Okay, so we have this partial C, partial Q, and then we have delta Q here, all right? Then we have a certain number of higher order terms. This is the first higher order terms, and it goes higher and higher, but we don't care about that. Actually, we only care about, this guy and this guy. I'm making an assumption that, Taylor series will have close representation of original equation, but just using these two components, that's the way we can find the solution for our set of nonlinear equations. You with me? Kind of. Okay? Now I'm making that assumption, so this is my original Taylor series, and I'm neglecting this and all other higher terms. I don't care about that. All right, so what is left is this one here, my first two components, and that's equal to 0. That's how I can express my equation. All right? So we are after this guy here. So we are after this delta Q. That's what we really wanted to solve. So how is it we can solve that? Well, we can solve it by taking, first of all, this vector, put it in our right-hand side of the equation, which make it, minus C. And then I'm going to take this one here, and I'm going to invert it and put it in the right-hand side of the equation. Mission accomplished. Then I have this Newton difference as it is written here. Now, the one that is critically needed in this process is this matrix here. And this matrix comes from the partial operations. So it's a partial C, partial Q. So I'm differentiating my all constraint equations with respect to my all generalized coordinates. And that will give me a matrix, and the matrix is called Jacobian matrix. And now with help of Jacobian matrix, I could give a direction where the system is actually, where the coordinate is supposed to be at a certain time step. That's what I'm following here. Complicated? It's a little bit complicated. It's a little bit complicated, but believe me, what we're going to do a little later today is that we will go and solve the response. So we will take this whole system. We can write the equation for random mechanical structure, and we will solve the response based on the kinematic analysis. All right? Any thoughts? Any questions? Not today. Sure, I'm able to explain that. So, the core material, that, by the way, was an awesome question. Can we hug? Okay, no need to hug. Okay, but extremely important question, because we have to have a full understanding about what's a Jacobian matrix. And I'm thinking this mathematics will not do the job. I don't think that you can understand that no matter how hard that I'm explaining, is a partial this, partial that. It's still like, the way you're going to learn it is like, so don't worry to understand that. So my proposal is this. Let's look at numerical examples. Because with help of numerical examples, you get an idea, okay, that's the Jacobian matrix. Because then what comes a little later is a in-class quiz regarding the nature of Jacobian matrix. I'm asking, what is a Jacobian matrix and what is a physical interpretation of Jacobian matrix? You're supposed to be able to answer that to me. Can you answer it already? No way. Absolutely no way to understand that or answer that question this time. But let's look at the example. Is it all right? Okay. So, by the way, this is how it looked mathematically. So I'm sure this is making the chaos even worse than it is at the moment. So this is a mathematical expression of Jacobian matrix. And let's look at this few seconds. So what I have here is a matrix where the matrix rows match the number of constraint equations. So here I have the first constraint equations, and the first constraint equation is differentiated with respect to generalized coordinates. Let's look at an example in a second. Then I have here second constraint equation and all the way to NC constraint equations. Columns correspond the number of generalized coordinates. So this is my first generalized coordinates, which typically is Rx of body A. This one here is the second generalized coordinate, which is Ry body A, and so on and so on. This includes all the generalized coordinates. Now, based on the dimension of Jacobian matrix, I can already tell what's the number of degrees of freedom. How that's possible? It's possible because the number of columns is equal to the number of generalized coordinates. Remember that the number of degrees of freedom is computed in such the way that n minus nc. The number of columns is equal to the number of generalized coordinates. So it gives me this value here. Number of rows is equal than the number of constraint equations, which gives me this row here. Now if we go just shortly back to this slide here. Now look what I have in this slide here. Here I have to invert Jacobian matrix. You know that you only can invert the matrix if it is positive definite skewer matrix. Skewer matrix means that there have to be equal number of rows and columns. Only scenario where you have equal number of rows and columns is a system where the number of degrees of freedom is equal to 3. No, let's say it again. So number of degrees of freedom is equal to 0, not 6, but 0. Okay, so because 0, because let's go back here. Because this one here corresponds to a number of generalized coordinates. This one here corresponds to a number of constraint equations. Have to be skewer matrix. Otherwise, you cannot invert it that. All right? That's mathematics. Should we leave mathematics behind and let's look what means that we can do this in practice. Okay? Sounds good? All right, so this is our favorite guy. So this is our mechanical system, which consists of one moving body. And the one moving body is a beam-like body, as shown in this figure. And the beam-like body is constrained in 2 locations using primitive joints. So we have practiced this before. So we have created the constraint equations for this system before, but that was actually last week. All right? So I have primitive joint here, another primitive joint here. And now based on this information, I can create the constraint equations. And there's going to be two constraint equations. One associated to this point, another one associated to this point. All right? That's how it's going to be. Now, we're going to simply go back to our notes from a week back, and check how was the constraint equations. We wrote it a week ago that the constraint equations are like the ones shown here. So the first constraint equation is going to be Rx associated to body A, which is the only body I have in the system, L divided by 2 multiplied by cosine theta minus D. All right? And then the second constraint equation is Ry, body A, minus L divided by 2 multiplied by sine theta. Again, go back to your notes and check how we create these constraint equations. All right. Now what we will do next is that we will create the Jacobian matrix for this system. What is that we need? So we need to know all the constraint equations. We have that already. So we have these two equations, C1 and C2. There is no more constraint equation than these two. Then we need variables. So what are the variables? That's generalized coordinates. So what are the generalized coordinates in this system? How many there are? How many generalized coordinates in a planar system where there is a one moving body? 3, correct, 3. And these three coordinates are Rx, Ry, and angle theta. All right? So next is just the pure mathematics. No thinking, just math. So we will take this equation. We will first differentiate this equation with respect to first variable. Okay? So it's going to be parcel C1, parcel Q1. Q1 is this guy, Rx. All right? So I'm going to take this equation, I'm going to differentiate that with respect to Rx. What's going to be my solution? It's going to be 1. Nothing else, because Rx only appears in this component. And when I differentiate that with respect to Rx, I will get 1. Right? Yes? No? Yes? Don't know? Okay, so it's yes. Yes. Okay, next one. I will take the very same constraint equation. This time, I will differentiate that with respect to second variable, second generalized coordinates. What is our second generalized coordinates? That's, let me change the color, this one. That's our second generalized coordinates. Now when I differentiate this equation with respect to this one here, it's going to be 0. Because Rxy is not mentioned anywhere in that equation. So it's going to be equal to 0. Final. The final generalized coordinate is this guy here, angle theta. And now when I differentiate this equation with respect to angle theta, this is the only component where the angle theta appears. So it's going to be minus L divided by 2 sine theta. Make sense? Doesn't need to make sense, because this is just math. And remember the promise we made in the first lecture? No thinking. The multi-body dynamics is not about thinking. It's just the mechanical steps we have to repeat over and over again. This is how we're going to create, the solution for our, whatever is our problem. So whatever problem you have in your life, follow the multi-body dynamics. That's the way you can solve it. That's my advice. Problem with the spouse, follow the multi-body dynamics. Problem with, I don't know, any other problems, that's always your solution. You're with me? You know how to solve your life? Not that, but do you know how to solve multi-body dynamics? A little bit. Okay, so we are kind of in the beginning of the process. Okay, next one. We're going to take this constraint equation and we will redo the whole thing. Redo the whole thing. Very, very mechanical. No thinking. So we will take this equation and we will first differentiate that with respect to what? This one. First generalized coordinates. What's going to be the solution? 0. Because the Ry is not mentioned in this equation. Rx is not mentioned in this equation. Then I differentiate that with respect to Ry. Here it is. So it's going to be 1. And then finally, with respect to angle theta, so now it's going to be minus L divided by 2 cosine theta. That's my Jacobian matrix. Now, what's going to be the number of degrees of freedom based on Jacobian matrix? Okay, how many columns I have? How many? 3, okay. 3 columns. How many constraint equations? 2. How did you know that? Because of the number of rows. Correct. 1, 2. 2 rows. The number of degrees of freedom is 1. Okay, that's how it goes. So, can we solve the response of this system by using kinematic analysis? We cannot. Why? Because remember, in a kinematic analysis, we have to invert Jacobian matrix. How are you going to invert something that is not the skew matrix? Okay, there's a little bit of technique in this direction, but we are not going to speak about that. Let's just conclude that we cannot. We cannot. So we have to have one extra constraint equations. One extra constraint equation could be driven constraint. Something that I'm saying that, okay, say point P here is no longer free to move along the global x direction, but instead it has to follow the certain constraint. Constraint could be, such that this coordinate has to be equal to sine time or something like that. And then this point will move because the motion is always stronger than the force. Always stronger than the force. So if I say the constraint, you have to stay there. It will stay there no matter how big force will try to take it away. It will always stay in a location. Remember, in a revolute joint always will be combined into bodies, no matter how other forces try to separate it. So there is no big forces in this planet that can overview or that can overdo the constraint equations. So the biggest power we have is the constraints. All right? So that's the biggest power in the universe. Constraints. What comes next? Forces, moments. But right after the constraints are bigger than that. All right? You with me? Good. So, Jacobian matrix tells you what? Physical dimension of the body, color of the body, number of degrees of freedom, how forces are imposed to the body. This time, I'm feeling it. I'm feeling it. Do you feel the same? It will happen today. It will happen. It will happen. Is it on? Can you see that if it is on?
Yes.
Today is a day. It will happen. Okay, are you guys ready? Okay, if you're shy about this, go and discuss with your fellow student. Please, please. Only one is correct. Only one. Only one is correct. Others are nonsense. Others are absolutely nonsense. I'm scared. A little scared. But I'm still feeling good. I'm feeling good. Okay. And I still owe you, by the way, I owe you a coffee, I think, because you guessed last time the percentage correctly. I think it was you. Yeah.
It was me again.
Yes. Okay, what's going to be percentage today?
90.
Yes, 100. 100. 100. Yes. 110. 100. It's going to be 100. Okay?
I think 97.
No. It will be 100. It will be 100. Okay, so we have 64 students 66 students. Okay, how is that we're going to celebrate this 100% success rate? Are we going to make a party some kind? But you don't know. You don't even know how we're going to do the celebration. Whew. Now, if it's going to be 100%, you need to take a picture, and I will show the picture director. Look at me. You know, I'm really outstanding student. As teacher, you know, everything is 100% here. Everyone knows what's the deal with this. Okay. 4 students are still thinking. You guys done? Yeah. Online participants, I hope you're done because, so one more is missing. Maybe that was just someone that is slipping at the moment. And it's going to be within the 3 seconds. 3, 2. Okay, 1. And yes, look at this. Okay, but okay, good news is this. I have some good news. Look at this. 89% of students knows that the Jacobian matrix tells number of degrees of freedom. Another very good news is this. No one is saying that this defines the color of the body. So it's, I'm very happy. So you're learning multi-body dynamics. Obviously, you're learning that big time. Okay, physical dimension of the body. No, we haven't discussed about that. We have not discussed about that. You cannot define that based on the Jacobian matrix. D, check your notes. There be no discussion about the forces so far. I have only mentioned that there are something called forces, but you have no idea what the forces means in reality. So that's why the forces are the question. They are the question. Okay, so let's practice a little more. Okay, this is the algorithm you have to follow in order to solve the kinematic responses. So you will get started by first deriving the constraint equation and compute the Jacobian matrix. It's very mechanical work again. You just make things to happen. You will get this matrix, and then you will calculate the Newton difference based on this equation. So you're going to go and invert the Jacobian matrix. You will take the vector of constraint equations, and with those 2 pieces of information, you can solve the Newton difference. So it tells you how to update the generalized coordinates in order to reach the final destination. What's the final destination? That's the solution at one particular time, position level. All right? Then I will go and update the generalized coordinates with help of Newton difference. So I'm going to have the generalized coordinates and I will add something to them. And I will add the Newton difference to my coordinates because they will tell me where to travel. Okay? So I will reach the new destination, which is updated generalized coordinates based on the Jacobian matrix and constraint equations. Now I'm going to use this one here to compute the Jacobian matrix and constraint equations again. Constraint equation, by the way, not mentioned, but you have to do that. Then you will go the final step and you check how small is the Newton difference. And if the Newton difference is having the numerical values that are very small, then you can make an assumption that I have reached the destination. Because now the difference from my desired destination and my current destination is next to nothing. It's within the certain predefined tolerance. Okay? If that's the case, you stop. You're ready. You have the position solution at one particular time. And if you don't, you go back here, you keep on updating your coordinate until you reach the final destination. Makes sense? We will practice that in a second. Okay, then what about these other levels? What about velocity and acceleration level? Well, that's just a pure math. We're going to simply take the constraint equations. Excuse me, this one here. This is our original constraint equation. And we will differentiate that with respect to time. And this is just the pure math. And we will get C dot, as mentioned here. So C dot, and what's because of what comes because of the C dot, then we have here Jacobian matrix multiplied by velocity of generalized coordinates. And then this is a constraint equation that is differentiated with respect to time. Details, not mentioned here, but this is just math. Go and check the lecture notes if you're interested about details. All right? Then another step forward is acceleration level. So I will go and take this equation, this one here, and I will differentiate that one more time with respect to time. So I will get here Jacobian matrix multiplied by acceleration of generalized coordinates. Then I have here, constraint equation that is differentiated twice with respect to time. And then I have here monster, which is a Jacobian matrix multiplied by velocity of generalized coordinates, and that gives you a vector. And that vector you will differentiate one more time with respect to generalized coordinates. And then you get the solution, which is a matrix. And that matrix you finally multiply by velocity of generalized coordinates. We will practice that in a second. And then I have here one more component where there's a Jacobian matrix that is then differentiated with respect to time. And then that's multiplied by velocity of generalized coordinates. That's the one you can then use to solve accelerations. All right. No need to memorize any of these details because, again, in written exam, you can have all the notes with you. So if I will ask something related to this equation, go and check the notes. Go and check the recordings. Go and check the PowerPoint presentations. So no need to memorize it. But please memorize the concepts because those are important. Okay, so I'm ready to move on to this is the final kind of like a kinematic analysis summary. So this is where I get started. So my time is equal to my starting time, which typically is 0. I will first conduct my position level analysis. I will do that with help of NewtonRaphson. So once I'm done with that, then I'm ready to move on to velocity analysis. I will compute the velocity based on this equation. And finally, I will compute the acceleration based on this equation. And then I will go and increase the time and redo the whole thing. So again, here I have an iteration within this step. So I go back and forth until I reach my final destination. Then I'll be ready to move on here, which is just a substitution. Here is just a substitution, a little more complicated, but still a substitution. And then I'm ready to redo the whole thing. That's how you can solve the kinematics. How it sounds. You ready to practice? By the way, there's no break today. And that's because I need to be off soon. So, is that a good news or bad news? Good news, definitely. Okay, so let's practice. Okay, remember this guy, or this example with the one moving body. Now what I will do next is I will constrain this one moving body, this body, in such the way this point Q is no longer free to move along the global x-axis, but instead it has to follow this equation, which is a sine time. So this t here is a time divided by 4 minus 1 divided by 2. That's my constraint. It's a driven constraint. I'm forcing this point to follow this equation, and it will follow no matter what. And now I will use the kinematic analysis to solve how is the response of the system because of this. The information that I need to conduct this is a constraint equations, because they will tell me how is the rest of the configuration. This one here only tells me how this particular point is moving. But other constraint equation will tell me the fuel configuration of this system. And then I will solve this by using a kinematic analysis. You're ready? Okay. All right, so this will get started from the very beginning. So we will first derive the constraint equations. So the first constraint equation we have to look at is going to be related to point Q here. How are we going to introduce the constraint associated to point Q? By using this equation we are very much familiar with. This is the one we will use again. So what is that telling you? It's telling that you will get started here from the origin of the global coordinate system. You're first going to travel to body reference coordinate system. That's defined by vector r. Right? You're going to account the orientation of the body reference coordinate system with help of 2x2 rotation matrix. Makes sense? And then you will go to this final destination Q by with help of vector u bar. That's it. Then you reach this point here, and then you will tell how this point will move. All right? So this is my equation. So I have here translation of the body reference coordinate system, orientation of the body reference coordinate system, a vector u bar. How are the constraints? Y direction, the motion in the global y direction, that must be equal to 0. Must be equal to 0 because I have here primitive joint that says motion this direction is not allowed. All right, so that's why this has to be equal to 0. What about the motion in a global x direction? What's that? That's defined by that driven constraint. It's a driven constraint that forces this point to move in a certain way. What way? That's defined in this equation. So I will take this equation and put it here. All right, so then I will just solve this equation. I will get two constraint equations. Now this is a little bit of other information. So vector u bar will consist of x component, that is L minus L divided by 2, because the x-axis is pointing this direction. In order to travel here to here, that's going to be L divided by 2 minus direction. Clear? Y direction, that's going to be equal to 0. So with help of those information, I can express my first two constraint equations as it is shown here. My third constraint equation will be associated to point P, that particular location. How can I make that happen this time? Surprising, we're going to use, yes, this equation again. Okay, so we're going to first travel here, then we're going to go take account the orientation of the body reference coordinate system. We're going to go to this point P with help of vector u bar. Right, so that's it. And now the constraint will be such that the motion in the x direction is constrained, the motion in the y direction is free to go. Okay, let's look. So that's going to be my constraint. So motion in what this says, motion in x direction. Yeah, motion in x direction, that's correct. This motion in x direction, which is this direction, have to be equal to 0 because the way the global coordinate system is located, equal to 0. Okay, makes sense. Okay, what comes next is a pure mathematics. I will take each one of these constraint equations and I will differentiate then with respect to each one of the generalized coordinates. That's what I will do next. All right? So let's make it happen. So I will take the first constraint equation, not visible here, but that's how it reads. So the differentiated that with respect to Rx, that's going to be 1. Okay, so it's 1 here. Differentiated that with respect to Ry, that's going to be 0. And angle theta, that's my final component. Then I will take another constraint equation, I will redo the math. I will do this partial operation, I will get this second row, and finally I will get the third row. What's the number of degrees of freedom?
0.
How did you know that?
3 minus 3.
3 minus 3. Where this 3 is coming from? Because of the number of rows and columns. What is this? Skew matrix. What is that we can possibly, sometimes what we can do with the skew matrix is we can invert it. If we can invert it, what is that we can get? Newton difference. What's the Newton difference? Tells us how we're supposed to update the generalized coordinates to reach the solution. Make sense? We're getting close to solve this issue. Okay. All right. So that's my Newton difference. So this is how the Newton difference look like. So do you have to invert that? You know, that's a painful process. I am able to do that by myself using pen and paper. But that's why we use these symbolic math tools. Okay. Then this is my constraint equations. So they are listed here. 3 constraint equations. So I'm ready to compute. Is what? Okay, let's see. OBS is on. So it's all. I think it was only problem related to ear server. Is it looking all right? No.
Yes.
So we're back on.
Yeah.
Very good. Very good. All right. Look at this, by the way. Look at this. So I have these steps. You know, in order to solve the kinematic, so you have to follow the certain number of steps. So first step. Form the Jacobian matrix, and you know the constraint equations are needed in order to make that happen. That's your first step. Do that. So once you have that, then the second step is Newton difference. Compute the Newton difference. All right. Step number 3 is a velocity. Velocity is a very simple substitution problem. So we're gonna simply take the the equation shown in a few slides back, where I have here Jacobian matrix, again inverted, and then I will take my constraint equation and I will differentiate then with respect to time. You know, this is my original constraint equations, and now when I differentiate that with respect to time, there is only one component that is a function of time. What's that? That's my first constraint equation. So when I differentiate that with respect to time, this is what I will get. Time is not mentioned here or here, so that's why the second and third component are equal to 0. Make sense? Okay, so this is how my velocity can be solved. So it's a pure substitution problem. One step away from solving the response, and the one step away solving the response is acceleration. In acceleration, I need again Jacobian matrix, and I need constraints that are differentiated twice with respect to time, and then I need this monster guy, this guy here, that consists of Jacobian matrix, velocity, and differentiation, and then the velocity again. Let's make that happen first. So I have here Jacobian matrix that is multiplied by velocity of generalized coordinates. Look at that. So the velocities are just the vector of velocities, nothing else. When I do this math, so when I'm multiplying this matrix with respect to this velocity, I will get a vector as a solution. All right? So vector consists of 3 components. And then I will go and differentiate these 3 equations with respect to generalized coordinates again. That's my denotion to make that happen. So I will do this differentiation. Now I'm not going to solve the details this time. So this is what I will get as a result. Hold on. And then finally, I will multiply the solution with velocity of generalized coordinates. This is how my final result look like. Painful, but symbolic math tools will do it for you. All right. Then the final the constraint differentiated with twice respect to time, that will be shown here. And this guy where the Jacobian matrix is differentiated with respect to time will be equal to 0. because the Jacobian matrix is not the function of time. That's why. So finally, okay, my description of velocity is not shown here, but you can find it out by substituting everything to this equation. Now I'm ready to move on to MATLAB. Are you guys ready? Because this is going to be emotionally one of those highlights in your life. Okay, so it's going to be like getting married, solving the first kinematic analysis, you know, that level, getting first child. Okay, you ready? So let's put this in a MATLAB and see what's going to happen. Okay, so here, first of all, I have the MATLAB code that explains how everything is made. I think that I'm not going to explain the details here because, you know, I'm simply following whatever I did in my example. Go and check the files that are available in a Moodle database, but this is an operation that I'm doing. And I'm simply going to open the MATLAB and I will solve the response. You ready? Okay, now what I need to do is that I need to close their Earth server connection because otherwise I'm unable to put this VPN connection on. And I need to put